Hello, Anatomy and Physiology 2 students. This is going to be a demonstration for Lab 3 on the proper electrode placement. And what I'm going to do is I'm going to start off by showing you just a standard 3-limb EKG. Now the first electrode I'm going to start off with is the white electrode, and that's going to go here on the anterior portion of his right arm. Right wrist. I'm going to put the red electrode on the anterior part of his left wrist. And then I'm going to put the black electrode down here on the medial part of his ankle. And as you see, he has this triangle here, and that's what is referred to as Einthoven's triangle.
After this, I laid down for calibration and so that we could take my resting EKG. Here you can see it up on the screen and you can very clearly see my heart rate. And then after we took my resting EKG, we ended up doing a 20-minute exercise cycle, which allowed me to raise my heart rate up, and then we were able to compare that. So here you can see I did 20 minutes on the bike, and then after that I laid down again so that we could get the EKG of me lying down. So this is just like the other one, except this is after my 20 minutes of exercise. And then we're able to take the data from the post-exercise EKG and analyze that and see how it changes.
Hello everyone. I wanted to take a few minutes and go over some of the results and the data that we got in our last lab that I collected in Lab 3, and that was the EKG lab. And just as a reminder, the purpose of this lab was to look at the electrical activity of my friend Eric's heart using an EKG. And ultimately, what we wanted to do was compare the electrical events that were occurring during rest and that were occurring after 30 minutes of exercise and relate them to the mechanical events that were occurring. So to do so, I put the electrodes on Eric's wrists and legs, and I got something that looked like this. Okay. Now, just as a reminder of what we're looking at here, this is a zoomed in screenshot that I got from Eric's EKG. And this first wave here, okay, this upwards deflection is going to be your P wave, all right? And your P wave is what represents atrial depolarization, okay? Now this downward deflection right after your P wave is going to be your Q wave. That's going to go in and peak up to your R wave, which is an upward deflection here, down into your S wave. So this is known as your QRS complex, and your QRS complex is what's going to represent ventricular depolarization. All right. Now this next wave here is your T wave, and your T wave is what is going to represent ventricular repolarization. Okay, so you have your P wave, your QRS complex, and your T wave. Now, this is a picture that I got directly from your guys' lab. One of the things that we did was compare the duration of ventricular systole and ventricular diastole during rest and after 20 minutes of exercise. Now remember, ventricular systole, right here, is occurring when the ventricles are contracting and forcing blood out from the chambers of your heart into pulmonic and systemic circulation. Ventricular diastole, on the other hand, is going to be when the ventricles are relaxed, okay? And blood is going to be coming in to the ventricles from the atria through both the left and right AV valves. Now notice that this physical event of ventricular systole, of the ventricles contracting, doesn't start right here at the Q wave. And that's because it takes a little bit for this to occur. Remember, this is a measurement of electrical activity, the EKG, and ventricular systole and ventricular diastole are the mechanical events that are corresponding to these electrical events, okay? So You have ventricular systole starting here at the R wave going to the end of the T wave. And then you have ventricular diastole picking up right here after the T wave going to the next R peak. All right, and that's what we did. We measured those two parameters both before and after exercise. Some of these other parameters that can be measured, like the PR interval or the ST segment, or even the millivolts of the P wave or QRS complex, are important and usually measured in to diagnose some obscure dysrhythmia or an electrical problem with the heart, but we're not going to focus on that. All right. Now this table here shows the comparison between heart rate, ventricular systole, and ventricular diastole, both before exercise, during rest, and immediately after exercise. And remember, during exercise, the demand for oxygen is greater because your muscles are being used and starved. So cardiac output, which is normally about 5 to 6 liters of blood per minute, can be 3, 4, even 5 times greater in an individual who just got done exercising, which means your heart can pump 15 to 20 liters of blood per minute in some cases after you're exercising. But how exactly does it do that? So notice here that the heart rate is lower during rest and it increases during exercise, which is expected. But what happens to the duration of ventricular systole and the duration of ventricular diastole? Well, you could see that in Eric's case, ventricular systole stayed relatively constant, but ventricular diastole is what took the biggest hit. All right, and the major difference here is that the time that the ventricles spent relaxing or filling with blood. More blood filling the ventricles causes a greater stretch on the muscles within the ventricles, all right? Now remember Stirling's law. Stirling's law says the greater the stretch on the ventricle walls, the stronger the contraction will be. So because the ventricles are pushing more blood out, both the ejection fraction and the stroke volume are going to increase. Now remember, we defined stroke volume as the volume of blood being pumped out of the ventricles in one beat, okay? So what does this mean, all right? Well, considering cardiac output is going to be a function of the stroke volume and the heart rate, an increase in both the stroke volume and the heart rate is therefore going to increase cardiac output. So that's going to allow for more blood to be pushed out of your heart into systemic circulation so that your muscles can be fed the oxygen that they need. Now, next here, what I want to do, let me switch to a pen, is show you a quick, easy, and dirty way to manually calculate your heart rate, which you guys may be asked to do. So what I like to do is I like to start at a position here. It's easier just to start at like 12 seconds, okay? And I find an R peak that starts right at the time period that I want. So I'll pick this one right here, okay? So we have this R peak. Now I want to count for 6 seconds. So 12, 14, 16, 18, all right? So now I'm going to draw my other line. I have a section of 6 seconds here measured out. Now I'm going to go ahead and count the R peaks. We have 1, 2, 3, 4, 5, 6, 7, 8. So in 6 seconds we have 8 R peaks, which means we have 8 beats for 6 seconds. So if we want to convert that into a heart rate, which is heartbeats per minute, we're going to multiply the 8 beats in 6 seconds by 10. So we get a heart rate of 80, okay? And again, that's just quick and easy. Most newer machines and even older ones can do this for you, but I think it's important that you guys know how to do it yourself. Finally, that's all I really had for this video. Feel free to stop by Thursday during my able hours from 2 to 4 p.m. to ask me any questions about the lab or anything else that you may have questions about. You can also stop by during Bridget's office hours from 10 to 12. But we're both available by appointment and we're both happy to help you. So feel free to take advantage of that, and good luck.